Yes. So we are discussing about just a moment. Okay, so we are discussing about different aspects of the traction. Okay, traction system. So we are talking about in my last class. We are talking about different types of not different types. What is the basic configurations for the connections? Okay, for the connections of traction motor with our main overhead means enter the connection between overhead line to traction motor. Okay, so where that microprocessor based control also been discussed over there. Basically, we are talking about the different drives. Okay, DC drives or AC drives, whatever drives we are using. So how they control the drives. Okay, that's the important issue. Suppose you are fixing up the speed of the motor, so you have to give some reference value. Okay, but the reference value should not be. It's not possible to give it in RPM. So what you can do, you can give it by the equivalent voltage value or any other set value. Okay, so it may be any other in terms of gain or any other terminologies may be there. Okay, so you have to fix up the set value. Then what happened? Then if you want to change, if you want to control them, so you have to sense the speed of the motor. Okay, so there is a tachogenerator, any other sensing, any other sensor or transducer may be there. So you are fetching the speed. Okay, what is the rated speed? Not rated speed, actual speed. And set point tracking means you are giving the rated value. Okay, which speed you want to, means your desired speed. Okay, now you are getting that actual speed. Now we are processing them. So who will process the entire process? That we're talking about that microcontrollers. Okay, microcontroller or the microprocessor. That means they will process the details data whatever you are fetching. Okay, from your sensors and then processing them, and it will give the response to the actuator. Okay, suppose you want to if you want to control the motor speed, so what you need to do, you can control, you need to change the if you want to vary the speed, so you want to change the armature voltage value. Okay, sometimes you have to use the field weakening method. So all the process, so gradually it is coming. So what you need to do, you have to process that signal. Okay, process the signal, and then you are giving some value to the set points, and then set point tracking will be there. Okay, this is the basic idea about the control strategy. Okay, and you are able to control the control the speed of the motor. So here motor is there, you can see the encoder or resolver, means whatever you're getting that value. So speed you are fetching from there, or position, sometimes you are taking the positions. Here you are taking the current feedback. So your processing unit, so whatever the processing will be there, based on that your control structures. Okay, what kinds of controller you want to incorporate over there. Okay, that controller will be analyzed mathematically inside of your microcontroller, and it will provide the gate pulses through the driver that I am talking about, that actuators. Okay, so to your test system, and directly it's come to the IGBT panels or IGCT panel. Okay, or diode panels, it may be there. Okay, so based on your rating, current and voltage rating. Okay, and you are able to change the speed of the traction motor. Okay, so here we can see what are the different types of DC and AC motor for the tractions. Okay, so in case of direct current motor, here you can see different characteristics are there. So what are the first features? Based on that input voltage, sorry, based on your input and the output, means availability of the of your source and what type of load you need to overcome. Okay, so if your availability of the source is DC and you have to overcome that high starting torque. Okay, so definitely that which motor should be preferable from your end? Definitely it should be the DC series motor. Okay, instead of DC, other kinds of DC motor, suppose shunt motor. Okay, or compound motor. So DC series motor is for suitable for your permission. But still, right now the different other types of motor also been using for the traction purpose. But the preliminary thing is that availability of the source and what type of load you need to overcome. Based on that, you have to picking up your motor. You can also design some special type of motor for specially designed for that traction, that is also possible. Okay. Then this DC motor can provide high starting torque. Okay, so here you can see DC motor can provide high starting torque, and it can also possible to obtain the speed control over the wide range. Okay, so up to base speed you can also control, then above base speed field weakening method it is also possible. Okay, so wide range of speed variations, that is another motivation for selecting the DC series motor. This meter speed control normally simpler and less expensive. Okay, this is another benefit. So simple in that configuration and less expensive. Okay, so modern industrial drive. So you are making that several DC motor plays a significant role. Basically, if you're using that induction motor or any other motor, okay, special motor, end of the day, what you need to do, you have to configure that we are talking about vector control, scalar control. What is our representation? We are having some AC motor. Suppose AC three-phase AC motor. I think you are done through one subject, one not subject, some module of your generalized theory of machines. Okay, suppose generalized theory of your any of the motor is possible. So what we can do in this subject, so if you go through that subject, you can see that we are analyze entire process in different transformation modes. Suppose Clark transformation, Park transformations means your we are transforming the rotating magnetic field to some specific. Sometimes we are transforming it to the stator field, okay, stator axis. Sometimes we are transforming it to the rotor axis. So we are transforming them mathematically. So what happened in that vector control? So we are transforming that three-phase machine to equivalent d-axis component, q-axis component. It's look like your just like your DC machines structures. Okay, mathematically. Okay, so it having some d-axis structures, it having some q-axis structures. Okay, equations. Now you are able to control them. So end of the day, what happened? What kinds of motor you are fixing up for the traction? So end of the day, if you go for any other sophisticated control or any other complicated control with some good control strategies, with good controllers in the microcontroller or DSP based processor, so you have to control the motor such a manner just like a DC motor. Basically, mathematically, the representation will be like that. Okay. So that's why the modern industrial drives DC motor plays a significant role. That's why it is mentioned like that. Okay. Now both series and separately excited DC motors are normally used in the variable speed drives. Okay. But series motors are traditionally employed for the traction applications. Okay, this is our idea. So we are using the DC series motor for the traction system. Due to the commutators, okay, due to the commutator, DC motor are not suitable for very high speed. Okay, why? The requirement, maintenance, and we have to switch to the AC motor. So why? Basically, sometimes changing of the commutator, huge current changing are there. Okay, suppose one segment to another segment, but brushes are shifting from commutator one segment to the another segment. So definitely there is a exchange of huge current. Okay, so that may cause some additional losses. Some flashing will be there. So that's some hazard, additional hazard is coming. Okay, and if you go for that very drastic area, so there is a high chances for shorting to communicator segment. In between of them, some grooving is there. So if the moisture or any other dust will be connected in is deposited in between of them, so automatically it will be shorted. That may cause for some other reason. That may cause for some that can affect your commutator segment. Okay, that pollutions. With the recent advancement, okay, of the power electronics conversions, okay, power conversions, control techniques, and microcomputers application, the AC motor drives becoming increasingly compatible with the DC motor drive. So right now the AC motor drives are also getting familiar or also getting famous compared to the DC motor drives. Basically, that's controlling strategy and other kinds of features. Okay, suppose they are very compatible for working in that very drastic weather area. Okay, so also the future trend that towards the AC drives, DC drives are currently used in the many industries. Okay, so both the cases it is implicable. It might be the few decades before the DC drives are completely replaced by the AC drives. So by that virtue of that benefits of the AC drives, automatically it will replacing the DC drives. Okay. So any other important thing is that control rectifier. Okay. So control rectifier provided the variable DC output of the voltage with the fixed AC voltage, where the DC-DC converter can provide the variable DC voltage with the fixed DC voltage. Okay, so some basic features. I think these points, all points are known to you. Okay, basically you have already gone through the power electronics. Okay, due to the ability of the supply of the continuous variable DC voltage, like your DC-DC converter, okay, control rectifier and DC-DC converter made the revolution in the modern industrial control equipment in the variable speed drives. Okay, so that how to maintain the voltage, so how to vary the voltage of your across the motor terminal. So you are using DC-DC converter. Okay, suppose AC is there, now you are making that AC to rectified DC. Okay, then you are passing the DC to rectified DC to that pulsating DC. Rectified AC also known as the pulsating DC. Pulsating DC to the smoothing reactor. After that, you will get more or less constant voltage of that DC. Then you are passing through the DC-DC converter. Now you are having the ability to changing the output of the DC-DC converter. How to changing the output? By changing the gate pulse of that DC. Okay, now you are able to changes that output. So directly that output will be connecting across of your motor, and motor terminal voltage is changing. Okay, so by this way you are easily control that industrial DC drives. Okay. Now presently that intellectual power module also been connected. Okay, so different AI based thing is incorporated with your conventional system. Okay, then control rectifier is generally used for the speed control of DC motor. Okay, the alternative form would be the diode rectifier that follows a DC converter. So what are the different types of converters? DC converters, sorry, DC drives converters are there. Okay, so what are different types of DC drive based on their converter? So here you can see, okay, there are normally three types are there. Okay, so first one is single phase drives. Okay, second one is the three phase drives, and third one is DC-DC converter drives. Okay, single phase drive, three phase drive, DC-DC converter drive. Am I audible from your end? Hello?
Yes.
Okay. Is my slide is visible from your end?
Yes, sir.
Okay. So actually today I have logging through the browser. Okay, that's why when I am asking, please let me know. So some problem is there in Microsoft Team software. Okay, that's why I'm joining through the browser. Okay, so the red boundary is not coming to my screen. So if you facing any difficulties, please let me know. Okay. So here we can see the control rectifier with DC-DC converter FET drives. Okay, so control rectifier. So you know that the in the power electronics subject, so different rectifiers are there. Okay, so power electronics simulation lab is not till now. I think it is not. You will go to the power electronics simulation lab next year. Okay, means 8th semester. Okay. So where we can see, basically, I will take that lab. So you can see that different types of converters we are using. Okay. So it may be the control, it may be the uncontrolled. First one is the uncontrolled, then semi-control, and finally control. Okay. So if you see their mathematical derivations, okay, so there is some specific applications. Suppose where we need to use that totally uncontrolled. Okay, where we are using the semi-control, where we are using the full control. Okay, so there is some specifications, specific applications. Okay, suppose if you want to design some low-cost drives. Okay, low-cost drive means only that what happened in that some of the college having some very setup, maybe low-cost setup. Okay, they are only just asking for the DC motor running, speed control of DC motor. Okay, what they are doing, they are only taking that four mode diode, and they are connecting that four mode diode in that bridge configuration. Okay. Now giving the supply to across the mood diode, it will be DC, rectified DC, and directly that rectified DC is given to the your machines. Okay, DC machines. Okay, so and it will work and you can control the speed. Okay, and you can take some reading. Okay, so what basically, so what you can see, there is a the costing of the drives is very less. Okay, minimal nominal cost. But instead of that, mood diode means it's a power diode. Okay, there is some difference between power diode and analog diode, means signal diode. Okay, in terms of their doping. Okay, in terms of their voltage and current rating. Okay, so based on the different conditions, it may be different. Okay, so what happened instead of that move uncontrolled rectifier, instead of that uncontrolled rectifier, you can also connect some full control rectifier. But what will be the difference? Difference is that maybe the mode diode cost is how much? Maybe it is 50-60 rupees. Okay, per diode is 50-60 rupees. But if you go for that control switch, then it will take around that instead of 50-60 rupees, it will be the minimum 10 to 20 times for one solid state device, for one solid state switch. Okay, suppose you are replacing the diode, means diode is your high current and voltage rated component. So equivalent you are getting only for that ACR, maybe thyristor. So their cost is not so much different with your diode. Definitely it will different. Okay, but still it will be more or less 10 times. Cost is more than 5 to 10 times of your diode rectifier. Okay, so if you go for any other sophisticated device, suppose IGBT or IGCT, that is 10 times of your thyristor. Okay, so it's very costly. Okay, so you can understand. So based on your application, suppose you are designing cost efficient drive, so you can directly use can rectifier, normal rectifier, uncontrolled rectifier. But the control rectifier, suppose some sophisticated drives are required, so where you are also use that uncontrolled some control drive. Sometimes you are also use some semi converter also based on that cost and that zone of operations. For full control you can go up to motoring mode, then so based on that configurations. Okay, full, so motoring mode, regenerative braking, so all kinds of things are possible for the full converter, but diode rectifier only the motoring mode is possible. Okay, so these are the different configurations. Okay, basically different selection of your converter based on your application. Suppose single phase are required for, if the source is available, source is single phase, so single phase AC you can only use. If your available source is three phase, then you have to use for three phase rectification, three phase rectifier. Okay, but the output of the three phase rectifier, when you are making them when you are making them DC, that amplitude also very comparatively high of your single phase rectifier. So is that one is capable of your system? So that you need to cross check. Okay. So AC supply, here you can see AC supply, then you are doing the rectifications. Okay. It is your control rectifier. So if you changing the firing pulse, so why control rectifier? If you are changing the firing pulse, so that VA, that armature voltage can be changed. Okay, so changing of the firing pulse, that armature voltage also been reduced. Increasing of firing pulse means off time of that full control rectifier will be less. So definitely that voltage, our VA value will be less. So motor will be less speed. So speed will be less. So here you can also see that VF is your field voltage. Okay, so again you are giving some AC supply through the DC-AC direct bridge rectifier or the control rectifier that directly coming to the IF. So now armature coil. Okay, the nature of also field is also in coil. So if you are giving some pulsating DC, automatically you will get more or less constant value of DC. Okay, so that advantages are there. Okay, so control rectifier fed DC drives. Okay, now you are making that variable DC. Okay, how you are making them variable? By using chopper. Okay, so here you are using by mistake it is written AC DC. Okay, it should be DC DC. Okay, by mistake it is there. Okay, so it should be DC. Okay, not in AC. Okay, it will be DC DC. Okay, it will be DC. Yes. So what we can see over there. So for the chopper feed drives, you are giving some AC here. Okay, AC supply is there. So AC is converting. It's a direct rectifier. Okay, chopper circuit you can get the variable DC output with fixed DC input. So you are giving the direct rectifier is there. So direct rectifier can rectify AC to DC. Okay. Then here you can see the chopper circuit. So DC DC conversion. So fixed DC is coming and variable DC is there. Based on that variable DC, you are able to change the motor speed. Okay. So VA will be varying, motor speed also varying. And that field winding, it is normally same like that your previous case. So DC you are giving, sorry, AC you are giving, then it will be rectified to the DC, then through the direct bridge rectifier or the control rectifier, then you are getting the variable field voltage. Okay, so variable value of DC means VF will also be different, and you are getting the different value of field current, and based on it you are controlling the speed of the motor. You are able to control the speed of the motor. Okay, so I think you are able to understand the drives. So here you can see the basic characteristics of the shunt motor. So one subject was there in electrical drives. Okay, so I hope you are already gone through that subject. So I'm not going to repeat all those things. I'm just giving the very brief on it. Okay, so as it is important, so that's why I'm asking for it. Sorry, I am discussing for it. Okay, so what we can see here. Hello.
Sir, your slide is still at microprocessor control.
So slide is not changing.
No, sir.
Okay, just for a moment again I'm sharing the slide. That's the problem. If we join through that browser, that's the problem. Is it visible now?
Yes, sir.
Okay. Now slide is changing. Is it changing?
Sir, yes, sir. Yes.
Okay. Now we are here for the basic characteristics of that shunt motor. Okay, so what happened here? We can see the diagram of the shunt motor. So field is separate. Okay, so shunt motor means common terminal will be there. From the common terminal, that field also being excited as well as your armature. Okay, so you are giving the what is the basic expression of the motor, so that va equal to va equal to eb plus iara. Eb is your back emf. Eb equal to zn phi p by 60a. So zn sorry z phi p whole divided by 60a, that terminology you can make it constant. So how it will become? So eb equal to omega into omega is your n terms of your frequency, so 2 pi f. Okay, so omega and kv if. So directly you are getting the value of eb. Okay, so and you are getting the expression of the speed w equal to va minus raia by kv if. So very simple one. Okay, so instead of if you are replacing that vf by rf. So here it is your if. Okay, if is there, field current. Now that vf by rf is coming, that is your if. Okay, so if you want to change the speed, so what you need to do, you can change that IARA. So additional resistance you can put the series with your armature. So that can be reason for additional drop of that armature voltage. So directly you can see the motor speed is able to change. So controlling of that what of the process varied by the controlling of the armature voltage VA, known as that voltage control. Then controlling the field current IF, which is known as the field control. Okay, or torque demand. Okay, so torque demand which correspond to the armature current IA for a fixed field current of that IF. Okay, these all are the very common ideas. Okay, so from where directly the motor speed can be varied. Okay, next one is the speed, which is the correspond to the rated armature voltage. Okay, so by using the field current and the related armature currents, known as that rated speed. Okay, so rated values of all the component, what speed you are getting, that is your rated speed. Okay, so here you can see that from the rated speed, that it is your base speed or the rated speed. Okay, that dotted line is your rated speed of the base speed. So up to rated speed, okay, so your torque is constant. Then after that, torque is varying. And here you can see that up to rated speed, what you will do, the power is also increasing. After that, power is getting constant, PD. Okay, so this is your armature current. Armature current is more or less fixed, and IF is fixed up to the rated speed, that is constant torque region, and after that it is your constant power region. Okay, at the constant power, power is, you know that power is changing. Field current is decreasing. Okay, so here you can see torque is varying and here the field current is varying. Okay, so what are the basic characteristics from the shunt motor drives? From that diagram you can understand. What is the speed? Okay, speed is less than the base speed. Okay, a speed is the less than the base speed. So what you can do, you are controlling the armature voltage. Okay, you are changing the armature voltage to vary the motor speed. Okay, and the armature current, okay, and the field current are maintaining constant, okay, to meet the torque demand. Okay, so the armature voltage VA is varied to the control of the speed. I think all of you will understand. So at that value, what you need to do, armature current and the field current are maintained constant to meet the torque demand, and the armature voltage VA is varied to control the speed. Okay, for speed, okay, for speed higher than the base speed, okay, for speed higher than the base speed, what you need to do, armature voltage is maintained at the rated value. So armature voltage is maintained at the rated value, and the field current is varied to the control to control the speed. These all are the very basic. Okay, so another thing is that power developed. How much power is developed? That you know, the torque into speed, T into W. That is your power. Okay, remain constant up to base speed. Okay, after that it will vary. So figure below the characteristics of torque, power, and armature current for the field current against the speed. I hope all of you will understand. So this is the very basic of your DC machines. Okay, so I think most of you are aware about it. Still, I am recapping. Basically, it's related to our study. That's why I have to discuss that point. Okay, so here you can see for that series motor drives. Okay, so in case of series motor drives, what happens? You can see there's motor speed omega equal to how much it is coming? Omega equal to VA minus RA plus RF whole into IA. Okay, so additional this is your field resistance and armature resistance. Okay, and whole divided by KVIF. Okay, so in this case, you know that torque equal to IV into what? Phi. Okay, proportional to K phi kV 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 omega sorry kV phi IV. Okay, now for that series motor, phi also being the directly proportional to your current. So torque is directly proportional to I square. So they are in parabolic in nature. Okay, that we can observe. Okay, from this one. So here you can see the very basic of that DC series motor. This is armature winding, field winding, and it's your armature, and it is your load. So load torque definitely it will be opposite to your motor torque. Okay, if the omega means motor is rotating, TD is your load that. So countering with your TL, okay, motor torque. The motor speed, okay, so the motor speed can be varied what? Controlling the armature voltage VA, known as voltage control. Next one is that armature current, which is the measure of the torque demand. Okay, so here you can see TD, okay, torque is there, okay, first constant, then varying torque, then current also constant, direct proportional to the current. So after that, it is also varying armature current. Okay, so power is linearly increased, then constant power region. So it is power is fixed. It is constant torque region. So that's why motor torque is fixed. Okay. So this zone is known as constant torque region up to base speed, and above base speed it is a constant power zone. A series motor can a series motor can provide a higher torque. Okay, especially for the starting. So in case of traction, what happened? We have to think about the static friction, means friction. So initially starting condition, huge torque are required. That can only given by that series motor, and in case of induction motor, so we have to vary the resistance. If possible, we can get it. Okay. And for this reason, the series motor are commonly used for the traction application. This is the basic reason for traction application. Here we can see what are the very basic characteristics of the series motor. Okay, so very basic characteristics are that first the torque is constant, then power is constant. Up to base speed, torque is constant. So speed up, okay, speed up to the base speed, armature voltage is vary, and the torque is maintained constant. Okay, so speed up, and gradually that armature voltage is varying. Okay, and torque is making constant. So that's the constant torque region up to base speed. Okay, once the related armature voltage is applied, okay, sorry, rated armature voltage is applied, the speed torque relationship follow the natural characteristics of the motor and the power. So torque into speed, which is your power. Okay, it should be the constant. After base speed, power is constant. So torque into speed. Okay, so if you make the speed fixed, okay, then torque will be vary. Or if you make the torque speed, so speed will be vary. Okay, as the torque demand is reduced in this period, okay, in the speed increases. Okay, at the very light load, at a very light load, the speed could be very high. Okay, so and it is not advisable to run this series motor without a torque. That's the reason. Okay, so at very low value of that value, so very high load. Okay, torque will be very high. Sorry, speed will be very high. Okay. So now operating modes for what? With that motoring mode. So different modes are there. Okay. First one is known as the motoring mode. Second one is the regenerative braking. Okay. Third one dynamic braking. Fourth one plugging, and fourth quadrant operation. Okay. That is full bridge mode. Okay. What are the different modes of operations? Okay. So variable speed applications. The DC motor having different modes that I have discussed already, starting off already. So what is motoring mode? So you know that in my last to last class actually, we're discussing about the motoring mode, then regenerative braking mode, okay, dynamic braking mode. So all those things we are discussing over there. Okay, so what happened both motoring mode, so arrangement of the motoring mode, here you can see for the separately excited DC motor, motoring mode for series motor, how it will be look like that. Okay, so motoring mode of operations, so where the back EMF EG, okay, back EMF EG is less than of your power supply. That's the idea. Motoring mode, that what is your power supply? VA. Okay, so here what is your power supply? VA is there for series motor, and generated EMF, that EG, is less than of your VA. That is happening in motoring mode. For the regenerative braking, that EG value is more than EA. How is it possible? EG value. So if you make the motor speed is more than your rated speed, so you are coupling that motor with another motor. Okay, then what happened? That combined speed will be very high. Okay, if you couple both the motor, their speed will be very high, and your EG value will be more than the rated value. Okay, and at that value of EG is gradually increase, and it can reach beyond the terminal voltage of the motor. So automatically that current, you can see that IA current. Okay, so IA current is there from low source side to load side. Here the direction of current is now source side to load side, means terminal of the motor, voltage terminal of the motor to the motor. Okay, if that IA current is more than your rated value, then what happened? So current flow will be reverse direction, not more actually. If that EG value is more than of your VA, so current will be flow from higher potential to lower potential. So direction of your motor current, means armature current, will be different, reverse one. So automatically current will be coming. So for this study, for this test, what we will do, we are using zero pointer, zero crossing meter. Okay, suppose IA can vary positive direction as well as negative direction. Okay, you can see that IA is coming negative side. Okay, so this configuration is very important. This is important for our circuit. Okay, so what are the operating mode? So if you want to go for the regenerative braking, then what happens in regenerative braking? So EG value is more than of your VA. Suppose that situation occur, then what happens? Directly that EG additional current will flow from motor armature to that source of the motor. So that is, and for the DC series motor, what happened? That is violating the flow of current through the armature field, or through the uh, motor field winding. So that can damage field of the motor. So what you need to do, you have to connect the changeover switch. So here the changeover switch is there. Okay, so here, okay, so directly it's connected, means what happened, the additional power, sorry, that if that current is different, oh sorry, potential and their magnitude is different. So additional power will coming from load side to source side through tapping of that through the tapping of that inductor. Okay, so what happened? What benefits you are getting? So it is not demagnetized. Okay, so it can save is span of the utilizations of the battery. Okay, operating modes. So regenerative braking. Okay, so the arrangement of the regenerative braking is shown in the figure. So here you can able to see the motor acts as a generator. Motor acts as a generator. Okay, as they are just like a generating components. Okay, so motor acts like a generator and develop an induced voltage EG. Okay, that EG must be greater than of your supply voltage VA. That is more than that. Okay, the armature current is now negative, but the field current is positive. That I am telling. So armature current is negative, but field current is positive. So one pointer is available in the market where the zero portion is inside of that tracking scale. Okay, then left side some of the scalings are there, and right side another scalings are there. Okay, so by that way you can understand. Okay, the armature current is negative, but the field current is positive. Okay, it's possible. Armature current negative, but field current is possible. Okay, field current is positive. The kinetic energy of the minor kinetic energy of the motor is returned to the supply. Okay, so kinetic energy that motor is supplied back to that, return back to the supply, as the series motor is usually connected series excited generator, self excited generator. For the self excited for self excitation, it is necessary that the field current aids the residual flux. So the residual, otherwise if you change the polarity directly, the residual flux got affected. Okay, so that's why you need not to do such work. You have to follow the standard method. This is normally accomplished by revising the armature terminals of the field terminals. Okay, so these are the very important points. Then what are the different operating points? So we are discussing about dynamic braking. Okay, what happened in dynamic braking? So the arrangement, you are directly what you are doing, that RB, okay, that is your braking resistance, dynamic braking resistance. So you are just connect, remove the load and connect the dial. So what happened? Additional energy is stored through that armature resistance and RB. Okay, the directly it is going. So for the failure of the the arrangement shows in figure are similar to those of the regenerative braking and constant the supplying voltage. Okay, so it's simple. Okay, and VA is replaced by the braking resistance RV. So RV is your braking resistance. Okay, the kinetic energy of the motor is dissipated by RV. So plugging is the type of braking, okay, but the component for plugging shown in figure. So here you can see the plugging diagram, okay. So the armature terminal are revised. Okay, sorry, the armature terminals are the reversed while running. Okay, so make when you want to change that one on a armature to a, so you have to change the pole field. Otherwise, it may be damaged. Okay, running condition at the same direction. Okay, the armature current is reversed, thereby the producing a braking torque. Okay, so we are getting a braking torque, and that may cause for deflection. For the series motor, either the armature terminals or the field terminals should be reserved, but both are not both. Okay, so these all are the very important features for plugging. Okay, so then four quadrant operations are there. So then single phase drive. So I'll start discussing about the four quadrant operation in my next class. Next class in on tomorrow. Okay. So before that, whatever I am discussing in my class, I can expect that my students also they are up to date. Okay, they are also preparing the class note. Okay, numerical problems. Okay, so all the things class note they are taking as well as numerical problem for their homework copy, and that assignment and the mathematics. What kinds of mathematics you are getting from you can solve it. Okay, so I hope you are getting my point. If you facing any difficulties any of that subject, so you please let me know. Okay, so today I am just concluding here. So in my next class means tomorrow I'll start from plugging. Okay.